In the 1920s, like long before smart thermostats and central air, the average home used roughly 125 kilowatt hours of energy per square meter per year.
Right, which is an incredibly low baseline.
Yeah, and then by the time we hit the 1980s, that number didn't just inch up. It didn't just double. It exploded to nearly 475 kilowatt hours.
A massive spike.
Exactly. We didn't get better at building homes. We actually just kind of forgot how to do it. We replaced architectural genius with, brute force, fossil fuel chugging air conditioners and furnaces.
We really did.
So, welcome to the deep dive. Today, our mission is to fundamentally change how you view the buildings you live and work in.
Because it's so important to shift that perspective, right?
Yeah.
From seeing a building as a blind, helpless consumer of resources to understanding it as a highly sophisticated, passive filter of environmental energies.
Yes, a filter. We are digging deep into an incredible stack of research today. It's anchored by this fascinating paper called Design Options and Passive Design Strategies, Part 1 by Nuno Dias Cortizos, along with some foundational concepts in bioclimatic architecture.
And it really is a profound shift in perspective. When you look closely at that exact phrase filter of environmental energies, it basically dismantles the way modern society has been taught to think about shelter.
How so?
Well, for the last 50 years or so, the default assumption has been that the environment is like an enemy. The building is designed as a fortress.
Right, just a sealed-up box.
Exactly, a hermetically sealed box designed to lock nature out completely. And because it locks nature out, it requires this massive artificial life support system to keep everyone inside comfortable.
Yeah, it's just this endless, really expensive battle against the climate. We pour concrete, we stack bricks, we seal it all up with glass, and then boom, we plug it into the grid.
And it just sits there.
Right. It sits there completely inert, pumping out air conditioning in the summer, blasting furnaces in the winter. But what really blew my mind in this research is the proposition that this is entirely backward.
It goes against everything we currently accept as normal.
I mean, what if your home could naturally regulate its own temperature? What if it could drastically cut its carbon footprint to zero and, save you a massive amount of utility money all without relying on heavy machinery?
To someone raised in a conventional modern home, the idea of a house heating and cooling itself without a mechanical hum in the background, it sounds like utopian science fiction.
It totally does.
But it's actually deeply rooted in fundamental physics, biology, and as you mentioned with that opening statistic historical precedent, we've successfully built this way for thousands of years.
Okay, let's unpack this.
Okay.
Because to understand where we were going with 21st century architecture, we have to deeply analyze where we went so disastrously wrong in the 20th century.
A very necessary autopsy, yeah.
Looking at Cortizos' research, there is this fascinating energy timeline. Let's go back to that early 20th century baseline, like 1900 to 1929. The data shows residential buildings using less than 125 kilowatt hours per square meter per year.
And their carbon emissions were sitting under 30 kilograms.
Right. Now, obviously, they weren't using high-tech solar panels back then. What exactly was happening at the architectural level to make them so incredibly efficient?
So what was happening was a complete reliance on what we call vernacular, traditional construction. And to be clear, this wasn't an aesthetic choice. It was an absolute survival imperative.
Because they didn't have heaters.
Exactly. Builders in 1910 did not have the luxury of a mechanical safety net. If you built a home that ignored the microclimate, like if you faced the wrong way or used the wrong materials, you simply froze to death in the winter.
Or suffered from heat exhaustion in the summer.
Right. It was literal survival design. You had to respect the environment because you couldn't overpower it.
So what did that look like physically?
They used locally sourced materials with massive thermal weight. We are talking about thick stone in the Mediterranean, heavy adobe clay in the American Southwest, dense timber in colder northern climates.
Materials that naturally handle the local weather.
Yes, they naturally mediated the extremes. The physical architecture itself, the thickness of the walls, the size of the windows, the angle of the roof, it had to do all the heavy lifting that a modern HVAC system does today.
The building was just inherently tied to its specific geography.
It couldn't exist anywhere else.
But then we look at the data for the mid to late 20th century. The graph in the research just spikes vertically. It peaks right between the 1960s and the 1980s.
The dark ages of energy efficiency.
Seriously,
Right.
Energy consumption skyrockets to that massive 475 kilowatt hours. carbon emissions hit around 110 kilograms. That is nearly a four-fold increase in energy demand.
It's staggering when you look at it.
I mean, what specific shift caused architects to suddenly build massive energy sieves?
It was really the collision of two major forces. First, an architectural movement known as the International Style, and second, the mid-century illusion of infinite, incredibly cheap energy.
Ah, the cheap oil era.
Exactly. The International Style, which was championed by figures like Le Corbusier and Mies van der Rohe, promoted this idea of a universal building.
Like a one-size-fits-all house.
Right. The vision was a sleek, perfectly rectangular glass and steel box that looked exactly the same, whether it was dropped into the freezing, wind-whipped winters of Chicago or the humid, stagnant swamps of Florida.
Or the blazing deserts of Dubai.
Precisely.
Which, I mean, when you think about it from a thermodynamic perspective, is absolute insanity. You wouldn't wear a heavy wool parka in Dubai and a swimsuit in Chicago.
You'd be miserable.
Yeah, so why would we dress our buildings the same way?
It was a kind of architectural arrogance, really enabled by mechanical engineering. Because around the same time, we saw the mass commercialization of powerful mechanized heating and air conditioning.
The active HVAC systems.
Yes. Suddenly, architects no longer felt obligated to design for the environment. They could draw a visually striking, transparent box, completely ignore the harsh sun glaring through the glass, and just hand the blueprints to an engineer.
And say, here, you fix the temperature.
Exactly. The mechanical engineer's job was to solve that resulting thermal nightmare by pumping massive amounts of fossil fuel energy into the building. The building became completely dependent.
And the research points out that this 1980s peak is exactly what the modern bioclimatic movement is trying to undo.
We have to undo it.
The 21st century architectural goal laid out by Cortisos is to become KW2 and CO2 neutral by the year 2025 and beyond. Like minimizing operational demand entirely through passive means and creating regenerative assets.
That's the terminology, yes.
But honestly, I have to play the skeptic for a second here.
Go for it.
You look at modern luxury homes, and the trend is all about sleek technology. If we are ditching the mechanized heating and cooling that defined the 20th century, aren't we just devolving?
Devolve.
Yeah, aren't we just returning to the caves, sitting in the dark behind thick, heavy stone walls?
If we connect this to the bigger picture, it is exactly the opposite of regression. This isn't about returning to the caves or abandoning human progress.
Okay, so what is it?
We are not abandoning technology. We are fundamentally shifting where the technological intelligence resides. Instead of putting dumb machinery into a poorly designed, ignorant box, we are instilling profound biological and climatic intelligence into the very form of the building itself.
So the house itself is the smart tech.
Exactly. A regenerative asset is highly advanced. It uses incredibly precise calculations of solar geometry, fluid thermodynamics, and material science to achieve human comfort.
Without the brute force of a compressor.
Right. It's an evolution from mechanical dependency to structural intelligence.
Structural intelligence. I love that framing. I want you, the listener, to think about your own home right now. Look around. Is it a 1980s energy guzzler fighting the environment, or does it work with it?
Most likely it's fighting it.
Yeah. Because if we want a building to work with the environment, the research makes it clear we have to start with the single most permanent decision an architect makes.
Location.
Right. You can always change your windows. You could retrofit insulation. But you cannot change your location.
Exactly. We are talking about the macro-scale microclimatic site strategy. You simply cannot fix a fundamentally bad location with good technology.
It's locked in.
The very second you decide where to place the footprint of a building on a piece of land, you have permanently locked in the environmental load that building will have to endure for the next century.
And the breakdown of topographical physics in this paper is so fascinating. Let's imagine a scenario. You buy a beautiful, sprawling plot of land in the countryside. It's got a high, prominent hill and a deep valley.
A classic challenging site.
Right. And the instinct for like 99% of people is, I want the grand view, put the house right on the absolute summit.
Which is a thermodynamic disaster.
The data paints a terrifying picture for a summit build. The wind intensity at the crest of a hill is 125% compared to the flat ground, and the thermal impact is a continuous drop of -3 degrees Celsius. Why is that wind so devastating?
It comes down to the mechanics of convective heat loss. Building on a summit exposes the structure to relentless high-velocity air currents.
Okay.
Now, every solid object naturally develops a microscopic boundary layer of still air clinging to its exterior
Like
surface.
a tiny invisible blanket.
Exactly, it acts as a natural buffer. But when you have 125% wind intensity constantly blasting the structure, it continuously violently scrubs that boundary layer away.
Oh, wow. So the house can never keep its coat on.
That's a great way to put it. The wind physically strips the heat right off the external walls faster than the heating system inside can replenish it.
So you're just bleeding energy.
If you absolutely must build on a summit, the passive design strategy dictates you cannot just plop a standard rectangular box up there. You have to use aerodynamic shaping.
Like curved roofs.
Yes, low sweeping profiles that deflect the wind. And you must plant heavy, persistent windbreaks, like rows of evergreen conifers. Otherwise, your mechanical systems will just run nonstop.
Okay, so the summit is essentially a wind tunnel that steals all your heat.
Correct.
So looking at my hypothetical plot of land, my next thought is, all right, let's build down in the valley. It's sheltered, it's cozy. The harsh wind will just blow right over us.
Also a very bad idea.
Yeah, Cortisos explicitly warns against valleys, too. The paper describes a phenomenon called nocturnal drainage, which honestly sounds like a bizarre medical condition.
It does sound terrible, and it can certainly be an architectural horror story if it catches a designer off guard.
How does that happen?
Nocturnal drainage is a beautiful, if invisible, demonstration of thermal fluid dynamics. As the sun sets, the air higher up on the hillsides cools down rapidly because it's exposed to the night sky.
Makes sense.
Now, basic physics cold air is denser and heavier than warm air. Its molecules are packed closer together. Because of this density, it literally obeys gravity.
Wait, it falls.
It flows down the slopes of the hills exactly like a liquid. It pours down into the valley, seeking the lowest possible point and settling into the depressions.
It's an invisible freezing river of dense air.
Yes, and because it pools at the bottom of the valley, those depressions become what climatologists call frost pockets. The ambient temperature there can drop 3 to 5 degrees Celsius lower than surrounding areas.
That's a massive difference.
But the cold isn't the only problem. Because valleys are sheltered and lack wind, moisture from the ground accumulates in that trapped cold air.
So it's wet, too.
You get heavy morning fog, persistently high humidity, and deep dampness. If you build there, the structure will constantly fight mold, a bone-chilling damp cold, and a severe lack of early morning winter sunlight.
Because the fog takes hours to burn off. So if the summit strips away my heat and the valley drowns my house in a stagnant, freezing fog, where on earth is the perfect spot to build?
The research defines the ideal construction site very precisely. You want a location that is naturally protected from dominant cold winter winds, remains well-drained, and is fully exposed to the sun.
So where is that?
Typically, in the northern hemisphere, this sweet spot is found on the mid to lower section of a south-facing slope.
Because you're elevated enough to avoid the nocturnal drainage, but low enough to be shielded by the hill behind you from the northern winds.
Precisely. And the thermal data is striking. A south-facing slope naturally receives about 110% of the baseline solar access in winter. It's tilted perfectly to catch the low winter sun.
So it provides maximum free heating before you even design the building.
Exactly.
There is another fascinating microclimate element mentioned. Proximity to a large body of water, like the sea or deep lake. The data states that a sea zone can provide a thermal amplitude dampening effect.
It's a very powerful moderator.
It can actually raise the base temperature by 3 to 5 degrees in the bitterly cold months. Now, I understand that a lake reflects light, but how does water actually keep a house warm in the winter?
It relies on a property known as specific heat capacity. Water has a remarkably high specific heat capacity compared to soil or rock.
What does that mean, practically?
At a molecular level, it takes a massive amount of solar energy to break the hydrogen bonds in water before it actually increases in temperature.
So it's stubborn.
Exactly. It takes water a very long time to heat up, but conversely, it takes an incredibly long time for it to cool down and release that stored energy.
So it acts like a massive environmental shock absorber.
That's it. A large lake or ocean acts as a gigantic natural thermal buffer. During a blazing summer day, the water slowly absorbs the solar heat without getting overly hot itself, keeping the ambient air relatively cool.
And in the winter?
At night, or during the onset of winter as the air temperature drops, that massive body of water begins to slowly release its stored heat back into the cold air. It severely dampens the extremes.
It shaves off the freezing lows and blunts the blistering highs.
It is quite literally nature's thermostat. And this brings us to a phrase you highlighted from the research, which I think is the golden rule of site placement.
Yes. Winter orient to the sun, summer steer to the wind. It's a beautifully concise axiom.
It should be the absolute governing principle before a shovel ever hits the dirt.
And what's amazing is that nature already knows how to execute this perfectly. The paper brings up this concept of biological intelligence utilized through landscaping.
Landscaping is crucial.
When we talk about architecture, we aren't just placing a rigid building on barren dirt. We are utilizing the living vegetation around it. Let's talk about the utter genius of a simple deciduous tree.
It's truly brilliant.
You go to architecture school and you spend dozens of hours agonizing over CAD software trying to design complex, motorized mechanical louvers to shade your windows perfectly.
And nature has already solved it.
Exactly. You read this and realize a standard oak tree is vastly superior to anything a human can engineer.
The deciduous tree is, without a doubt, one of the most perfect passive thermal filters ever evolved. If we analyze its performance throughout the year, it is flawlessly synchronized with human comfort needs.
How so?
In the height of summer, when solar radiation is intense and the building is at risk of severe overheating, the tree is in full bloom. Its broad, dense canopy of leaves provides profound, cooling shade.
It physically intercepts the heat.
It intercepts the shortwave solar radiation before it can ever strike your building's envelope. Furthermore, through transpiration, the leaves release moisture into the air, creating localized evaporative cooling.
Actively lowering the air temperature around the house. But then winter comes.
Yes. In the winter, precisely when the temperature plummets and you are desperate for solar heat, the tree responds by shedding its leaves.
The canopy just vanishes.
The bare branches now allow the low-angle winter sun to pass right through and strike your windows and walls. It is a dynamic, self-regulating, zero-maintenance shading device.
It is literal biological intelligence. Okay, so we found our ideal spot on the mid-level of the south-facing slope. We've planted our deciduous oak trees. We have our macro site secured.
Its foundation is set.
Now, we have to actually pour the foundation. What physical shape should this building take? Here's where it gets really interesting, because we are literally translating geometry into thermodynamics.
This is where we transition to the formal morphology of the structure. And the mathematical heart of this entire discussion is a crucial metric known as the form factor, or F.
Right. The form factor, as the paper defines it, is essentially the ratio of a building's external surface area, the total skin of the building, divided by its internal volume. So area over volume.
Correct.
Why is this specific mathematical ratio the absolute holy grail of controlling thermal loss?
Because the external surface area of a building, the skin, is the only physical boundary where heat exchange with the environment actually happens.
That's where the battle is.
Exactly. Every single square meter of exterior wall, roof, or floor touching the earth is a potential leak. It's a bridge for cold to enter or heat to escape.
So you want less of it.
If you have a massive volume of living space inside, but you've designed it to have a relatively small amount of external surface area outside, you have minimized the physical battleground. Therefore, absolute compactness is the ultimate goal.
The research uses these brilliant biological analogies to explain this concept, comparing architectural shapes to animal behavior.
Because animals have been managing their surface area to volume ratios for millions of years?
Right. The paper mentions the Saussure effect. This is the mechanism by which emperor penguins survive the lethal negative 40-degree Antarctic winter.
A phenomenal example.
If a single penguin just stands out in the open wind, its form factor is too high. It loses heat and dies. So what do? They huddle together in a massive, incredibly tight mass.
They reduce their exposed surface area.
Exactly. By pressing their bodies against each other, they drastically reduce the total exposed skin of the entire group relative to their immense combined volume. They are dynamically manipulating their form factor.
And we see the exact inverse of this behavior in hyper-arid hot climates. The sources note how desert lizards adapt their physical posture for thermal control.
Oh, to cool down.
Yes. To avoid lethal overheating on the desert floor, a lizard will purposefully stretch its body out or raise itself high off the hot sand using its legs,
Increasing its form factor.
deliberately maximizing its surface area exposure to catch whatever faint cooling breezes exist while simultaneously minimizing the conductive surface area touching the boiling ground.
And the most famous architectural equivalent to the penguin huddle is the traditional hemispherical igloo.
The perfect compact form.
When you think about the geometry, an igloo is just a sphere cut exactly in half. And geometrically, a perfect sphere has the absolute mathematical minimum surface area for any given enclosed volume.
You cannot get more efficient than a sphere.
By building a dome, indigenous peoples in freezing climates ensure there is the least possible amount of structural skin exposed to the wind. It minimizes heat loss to the limits of physics.
And offers incredible aerodynamic resilience. A blizzard wind simply slides over the curved dome instead of slamming into a flat wall.
But of course, as a practical matter, humans generally prefer living in rectangular spaces. Furniture is rectangular, building materials are straight.
We rarely build pure spheres for mass housing.
So when we design standard rectangular buildings, we have to calculate the optimal aspect ratio, the specific proportion of the building's length to its width.
And the critical insight from the research is that this optimal ratio depends entirely on the climate.
Right. The data explicitly points out that if you are building in a brutally cold climate, you want an aspect ratio of 1 to 1.1.
Which is practically a perfect square.
It's as close to a compact cube as you can get, keeping that surface area tight. But in a hot, humid climate, the optimal ratio stretches all the way out to 1 to 1.7. Why do we want a long, skinny building for high humidity?
Because in a hot, humid environment, your primary passive survival strategy is not retaining heat. It is inducing cross-ventilation.
You need the breeze.
You desperately need the breeze to flush out the oppressive heat and the stagnant moisture. If you build a deep, compact, square building in a humid climate, the wind simply cannot penetrate all the way into the deep center.
The air just gets stuck.
The air in the middle stagnates, humidity spikes, and the space becomes unbearable. By stretching the building out, making it long and thin at a 1 to 1.7 ratio, you drastically decrease the physical depth.
So the wind passes right through.
This shallow depth allows natural, gentle breezes to blow straight through the building from one side to the other. It creates constant air movement over the skin, which is biologically vital for sweat evaporation.
And then we look at temperate regions, places that have to juggle both extremes. They need to hoard heat in the winter, but aggressively shed it in the summer.
The most complex climates to design for.
The optimal rectangular ratio there sits right in the middle at 1 to 1.6. And I am utterly obsessed with the historical benchmark the paper provides for this. The massive urban reconstruction of Lisbon's Pombaline quarters.
The Pombaline Baixa is a crowning masterpiece of urban-scale bioclimatic design. In 1755, Lisbon was nearly obliterated by a catastrophic earthquake.
Followed by a tsunami and fires. It was devastating.
Yes. When the Marquis of Pombal took charge of rebuilding, he completely leveled the ruins and laid out a strict, highly rational grid system.
And they strictly utilized this 1 to 1.6 aspect ratio for the new city blocks. It's almost exactly the golden ratio. But it wasn't just for aesthetics, right?
Not at all. A block ratio of 1 to 1.6 in a Mediterranean climate like Lisbon's provides the absolute perfect thermal balance.
How does the block dimension actually balance the temperature?
The block is deep enough to provide sufficient thermal mass and temperature stability in the core during the blazing summer months, but it is shallow enough to allow ample perimeter surface area.
For windows and light?
This extended perimeter is critical for ensuring natural daylight penetrates the apartments, and crucially, it allows for essential winter solar gain. If Pombal had made the blocks any deeper, the center apartments would be freezing dungeons in December.
And if they were thinner, they'd overheat in July.
The 1.1.6 geometry captures the exact thermodynamic sweet spot.
It's incredible they intuitively codified that physics into city planning in the 18th century. The paper also weaves in a much more modern case study, the Drill House in Chile.
A brilliant modern application.
This house doesn't just use a simple rectangle. It uses a highly specific custom trapezoidal footprint combined with massive concrete columns rotated exactly 45 degrees.
It's using geometry to solve a massive environmental puzzle.
It maximizes the stunning visual views of the Pacific Ocean, but simultaneously, the angled shape and those rotated columns act as a dense physical barrier against the harsh coastal winds.
That is the ultimate hallmark of sophisticated architecture. The physical form of the building is not arbitrary. It is a direct, calculated response to the environmental forces on that exact piece of land.
Okay, so we have our optimal shape. Let's assume we have our 1 to 1.6 rectangular block. The next vital question is, how do we physically point this block at the sun?
Orientation.
Which moves us into what Cortisos highlights as the absolute lowest hanging fruit in all of passive design.
It is considered the lowest hanging fruit because it costs absolutely nothing.
$0.
Think about it. You take the exact same building design, the exact same materials, and simply by rotating its axis on the site plan to face the correct direction, you can yield immediate energy savings of 20% to 30%.
Zero additional construction cost, immense reward. And the absolute powerhouse of orientation is the south facade.
Assuming we are in the northern hemisphere, yes.
The paper breaks down what it calls the solar axis, which relies entirely on the orbital geometry of the Earth. Let's get into the physics here. Why is a vertical south-facing wall so incredibly efficient at catching heat?
It has everything to do with the angle of incidence of solar radiation. Because the Earth is tilted on its axis, the sun's path across the sky changes dramatically throughout the year. In the dead of winter, the sun's trajectory is very low on the southern horizon. Because it is so low, its light rays travel almost horizontally and strike a vertical south-facing wall almost perfectly perpendicularly.
At a 90-degree angle.
Yes. This direct, head-on hit maximizes the transmission of solar energy straight through the glass and into the building. The data shows that a south facade receives up to 3 times more winter sun than an east or west facade.
3 times more. That is a massive injection of completely free heat.
And the architectural genius of the south facade is that it continues to protect you into the summer.
How? Because the sun moves.
In the summer, the sun sits much, much higher in the sky. Its rays hit that vertical south window at a very steep oblique angle. Basic optics dictate that when light hits glass at a steep angle, a large percentage simply bounces off due to reflection.
So it rejects its own heat.
Furthermore, because the sun is high, it is incredibly easy to physically protect that window. A simple, short horizontal overhang or awning is all you need.
Like the brim of a baseball cap.
Exactly. It blocks the high summer sun completely. But that exact same small overhang is short enough to allow the low winter sun to easily sneak right underneath it 6 months later.
It's geometrically elegant. But this brings up what I think is a very common industry pitfall. You look at modern architecture, and the trend is massive floor-to-ceiling glass.
The glass box phenomenon.
The instinct is, well, if the south side gets 3 times more free winter heat, and it's super easy to shade in the summer, why don't I just make my entire south wall out of giant glass windows?
It is a very common temptation.
Why is that 100% glass strategy actually become a thermodynamic nightmare?
The physics of the building envelope will ruthlessly punish you for overindulging in glass. Cortisos is very strict about the 50-55% threshold rule.
What happens if you go over 55% glass?
The thermodynamic benefits hit a hard plateau, and the negative consequences severely compound. First, there is the massive risk of severe overheating, even in moderate weather. You've essentially turned the home into a botanical greenhouse.
Right, the shortwave radiation pours in.
And turns into long-wave thermal radiation, which cannot easily escape back through the glass. The air temperature spikes to uncomfortable levels almost immediately.
Okay, so overheating. What else?
Second, the insulative properties of glass. Even the most expensive triple-pane glass is a terrible thermal resistor compared to a standard insulated solid wall.
So it leaks?
Badly. While that giant glass wall lets heat in during the day, the moment the sun goes down, that huge expanse of glass will rapidly hemorrhage all the heat you just gained right back out into the cold night air. You lose all your gains.
That defeats the whole purpose.
And third, from a human-centric standpoint, massive eye-level windows create debilitating visual glare. You won't be able to work on a computer or read a book without blinding light piercing your eyes.
So we want the natural light and we want the solar heat, but we absolutely don't want the glare, the overheating, and the nighttime heat loss.
It's a tricky balance.
But the research introduces a brilliant workaround: clerestory windows and light shelves.
Yeah.
How do these manipulate the light?
A clerestory window is simply a row of windows placed high up on a wall, typically near the ceiling. Because they are high above human eye level, they instantly eliminate direct visual glare.
But they still let the heat in.
Yes. But their true genius is unlocked when paired with a light shelf.
Which is basically a solid horizontal ledge placed right below that high window, protruding into the room, usually painted a glossy white, right?
Exactly. The high-angle sunlight comes through the clerestory window, hits that reflective horizontal light shelf, and bounces directly upward onto the ceiling.
Oh, wow. So it reflects off the ceiling.
The ceiling acts as a massive diffuser. It catches that harsh directional light and spreads it out as a soft ambient glow deep into the interior of the building. You are capturing the solar energy and throwing it deep into the room.
All without the thermal penalty of a giant glass wall. It's using pure geometry to bounce photons.
Okay, so we've perfectly oriented our house to the south. The winter sun is pouring in.
We have the energy. But wait, if all that precious heat just hits a standard hollow drywall floor, the air will heat up rapidly, but the second the sun goes down, all that heat will vanish.
It will dissipate instantly.
How do we actually trap those photons? That brings us to what the paper calls the thermal battery.
This is a critical juncture. We must unpack the crucial dichotomy between thermal mass and thermal resistance. They do two very different jobs.
Let's start with thermal mass, or thermal inertia. We are talking about heavy, incredibly dense materials. Solid stone, poured concrete, adobe.
Heavyweight materials.
I want to use a financial analogy. Think of thermal mass like a long-term index fund. It absorbs your deposits slowly over the course of the day, holds on to them securely, and then pays out steady dividends of heat right when you need it at night.
I like that analogy.
How exactly does a concrete slab act like a battery?
The underlying physical property is volumetric heat capacity. Dense materials have the unique ability to absorb vast amounts of thermal energy without their own surface temperature rising too quickly.
So they just soak it up.
Imagine a thick stone wall inside your south-facing living room. When the winter sun shines directly on it, the stone starts drinking in that energy. But heat moves slowly through dense matter. It takes time to conduct into the core.
Right.
The physics of this delay is called thermal lag. The research notes that for optimal performance, a stone or concrete wall needs to be about 30 to 45 centimeters thick.
Why that specific thickness?
Because that precise thickness creates an optimal thermal lag of 10 to 12 hours.
A 12-hour lag. Let's trace that out.
Yeah.
The sun comes up, hits the heavy concrete floor at 10 a.m. The floor absorbs the heat all day.
Keeping the room from dangerously overheating.
Right. Then the sun goes down at 6 p.m. It gets freezing cold outside. But starting around 8 p.m., that floor starts slowly radiating the stored morning heat back out into the living room.
Exactly when the occupants need it most.
It is literally time-shifting the energy of the sun. You are banking the noon sun to spend it at midnight.
It is thermodynamic time travel. And traditional Mediterranean architecture mastered this principle centuries ago. They utilized stone walls that were sometimes 60 centimeters up to 1.4 meters thick.
Massive thermodynamic accumulators.
But in a Mediterranean climate, you have to survive blistering summers, too. To augment this massive thermal weight, they covered these heavy walls in white lime washes.
The classic brilliant white houses you see in Greece or southern Spain. The paper notes that these white lime washes serve as early cool coatings that reflect up to 89% of incoming solar radiation.
So the white paint bounces 89% of the blazing heat away instantly, and the massive stone easily absorbs the remaining 11% without the house getting hot.
It's a flawless passive system.
But as designers, we must also consider the systems of gain. How does the solar radiation interact with the thermal mass? The simplest method is direct gain, where the sun shines straight onto a floor.
But the sources also detail indirect gain, specifically the Trombe wall. I am fascinated by the Trombe wall.
Named after Felix Trombe.
It's basically a thick, dark painted concrete wall built directly behind a pane of south-facing glass with a small sealed air gap sitting between the glass and the wall. How does this differ from direct gain?
The Trombe wall acts as an engine. The sun passes through the glass and strikes the heavy, dark concrete wall. The surface heats up intensely, and because it is thick, it provides that long charge time to heat the room radiantly at night.
Okay, but what about the air gap?
Here is the dynamic part. The air trapped in that narrow gap gets extremely hot and highly buoyant. By designing small, operable vents at the top and bottom of the concrete wall, you create a thermosiphon.
Meaning the heat pumps itself.
Exactly. The hot air rises rapidly and flows into the living room through the top vent. This creates negative pressure at the bottom, which pulls cool room air into the bottom vent to be heated by the wall.
A continuous loop of convective heating powered by the sun. And a beautiful historical application of this is the Taos sun spaces in New Mexico.
Yes, attached solar greenhouses.
They built high-mass adobe walls separating the glass sun space from the main house. The heat soaks into the adobe all afternoon and bleeds into the house at night. This reduced heating demand by a staggering 40%.
It is incredibly effective, but thermal mass, the battery, is only half of the equation. The other half is thermal resistance, commonly known as insulation.
Right. If thermal mass is the index fund holding the wealth, insulation is the firewall. It stops the wealth from being stolen.
While mass absorbs heat, insulation fundamentally stops heat from transferring altogether. Materials with high thermal resistance are lightweight and full of microscopic air pockets like cellulose or natural cork.
Hold on, I have to synthesize this. If I need thick stone floors on the inside of my house to act as a battery, and I also need to wrap my house in thick insulation,
hmm
what is the correct order to layer these?
That is precisely the engineering challenge.
Because if I put the insulation on the inside, covering the concrete, the sun can't reach the concrete to charge it up.
Exactly. And this is where the paper introduces the hybrid typology. The strict rule is that you put the heavy thermal mass core on the inside, exposed to the living space, and wrap the insulation continuously around the outside.
Isolating your thermal battery from the outside climate, like a high-quality thermos bottle.
The hot soup is your thermal mass. The vacuum layer in the wall of the thermos is your insulation.
We have a phenomenal real-world case study for this. The Casa Corp project in Portugal. It achieved an incredibly low energy consumption of just 12 kilowatt hours per square meter per year.
From 475 down to 12.
Unbelievable. They build a heavy interior core and wrap the entire exterior in thick, natural cork insulation.
Cork is an extraordinary thermal resistor, virtually eliminating conductive heat loss. And in a Mediterranean climate prone to wildfires, wrapping your home in solid cork provides immense passive thermal efficiency and critical disaster resilience.
Because cork is fire retardant. I want you, the listener, to physically knock on the wall closest to you. Is it hollow drywall? Or is it a dense thermal battery?
Which naturally leads us to a highly critical modern problem. As we build better envelopes, we encounter a new paradox. If we build a perfect thermos, completely airtight with no leaks, we face a serious biological issue.
Sick building syndrome. The air goes toxic. We seal these buildings up so perfectly tight that VOCs off-gas from furniture, CO2 builds up from breathing, and humidity spikes. If a building doesn't breathe, it becomes a stagnant mold trap.
We've solved the heat problem, but created an indoor air quality crisis.
So how do we ventilate without noisy, energy-intensive mechanical fans?
We have to utilize natural aerodynamics. And the primary passive engine for vertical air movement is thermal buoyancy, known as the stack effect.
How does the stack effect work?
It relies on the principle that warm air is less dense than cold air. As air warms up inside a building, it naturally wants to rise. If an architect designs a continuous vertical space, like a dedicated solar chimney, they create an unobstructed pathway for this stale air to ascend.
And then it just leaves through the roof.
By placing exhaust vents at the highest point of this chimney, the rising warm air physically pushes its way out.
And nature abhors a vacuum.
Precisely. As that air escapes out the roof, it creates negative pressure at the bottom of the building. This suction naturally draws fresh, cooler outside air in through lower windows.
A completely free engine of ventilation. That handles vertical ventilation. But what about horizontal cross-ventilation? The specific rule in the text is that the distance between the air intake window and the outtake window cannot exceed 5 times the height of the room.
That is a critical geometric constraint. If your ceiling is 3 meters high, your building cannot be more than 15 meters deep from front to back.
If it's deeper than that, what happens?
The air velocity drops to 0 in the center of the building. The breeze dies, creating a stagnant dead zone.
Wait, the wind isn't just blowing straight through like a tunnel, right?
What's fascinating here is how the building essentially hijacks the weather through pressure differentials. It's Bernoulli's principle. When the wind hits the windward side, it creates high positive pressure, forcing air in.
And on the other side?
On the leeward side, it creates an aerodynamic wake zone of negative suction. That suction pulls the stale air out of the back windows. The positive pressure pushing and the negative suction pulling do the mechanical work of fans for free.
But what happens in extreme climates where the outside air is over 32 degrees Celsius? Bringing 35-degree air inside just turns your living room into an oven.
In those extreme environments, we utilize evaporative cooling.
Like placing a pond or fountain right outside the intake windows.
Yes, it utilizes the latent heat of vaporization. As the hot breeze sweeps over the water, a small amount evaporates. This physical phase change absorbs massive amounts of latent heat energy directly out of the air.
So by the time the breeze enters the window, its temperature has dropped significantly. Natural air conditioning, which brings all of these incredibly complex threads together into our conclusion.
The emergence of the transdisciplinary architect.
We've talked deeply about macro location, form factors, orientation, thermal batteries, insulation, and aerodynamics.
And the most important takeaway from Cortisos's work is that true architectural advancement is not about slapping technological gadgets onto bad designs.
You don't build a glass box facing west and then fix the overheating with giant AC units.
That is treating the symptom of a bad design with expensive bandages. True sustainability is curing the disease through fundamental geometry and physics.
The research makes it clear that architecture is a profound, polymathic synthesis of biology, climatology, and building physics.
And the human element must remain at the core. The research cites the J.B. Pierce Foundation's two-node thermophysiological model and the DISC index.
Which proves we are moving past just a simple temperature dial.
Yes, it deeply measures actual physiological responses: skin temperature in cold conditions and skin wettedness in hot conditions. Human comfort is a complex biological interaction with radiant heat, air velocity, and humidity.
So what does this all mean? When we put this entire puzzle together, orienting to the winter sun, using the exact right thermal mass, letting the building breathe, what is the ultimate goal?
The ultimate thesis is singular and profound. The architect's fundamental job is to remove the environmental load from the occupant's shoulders.
I love that.
The building should act as a highly sophisticated mediator. You shouldn't have to fight the thermostat, jump up to adjust blinds, or pay punishing energy bills just to exist comfortably.
The building does all the heavy lifting for you. It's beautifully empowering. As we wrap up this deep dive, I want to leave you, the listener, with a highly specific, lingering question to mull over.
A very relevant one.
As extreme weather events become increasingly frequent and grid stability becomes precarious around the globe, will passive design eventually transition from being a sustainable luxury to an absolute survival necessity?
It's something we all need to consider.
If the power grid goes down tomorrow in a freezing winter or a blistering heat wave, exactly how long would your current home keep you alive without a thermostat?
Thank you for joining us.
Thank you for taking this deep dive with us. Look at the walls around you differently today. Stay curious.